In this section, you will learn about increasing and decreasing functions and the first derivative test. First, we take a look at graphs of increasing, decreasing, and constant functions. If x2 is greater than x1, and that just means that x2 is to the right of x1, and f of x2 is greater than f of x1, now this just means that the y value at x2 is bigger than the y value at x1, then f is increasing. So as we go from left to right on the graph, if the y values are getting bigger, then that means it's an increasing function. And you can see this shape of a curve also means it's an increasing function because as we go from left to right, the y values are getting bigger. Now, if x2 is greater than x1 and f of x2 is less than f of x1, meaning the y value at x2 is smaller than the y value at x1, then f is decreasing. So both of these graphs are of functions that are decreasing. As we go from left to right, the y value is getting smaller. Left to right, the y value is getting smaller. Now, if f of x is equal to k for all x in an interval, then f is constant. So in this diagram, all the y values are equal to k. We get a horizontal line, which is the constant function. Next, we learn about using the derivative to determine if a function is increasing, decreasing, or constant. Let f be continuous on the closed interval from a to b and differentiable on the open interval from a to b. If f prime of x is greater than 0, which means the derivative is positive, for all x values on the interval from a to b, then f is increasing. On the open interval from a to b. So as we look at increasing functions, if the y values are getting bigger as we go from left to right, then that means the derivative is positive. If f prime of x is less than 0, meaning the derivative is negative for all x on the open interval from a to b, then we say f is decreasing. On the open interval from a to b. So for these decreasing functions, in both cases, the y values are getting smaller as we go from left to right, so that means the derivative was negative. If f prime of x equals 0 for all x on the open interval a to b, then f is constant. On that open interval from a to b. So for the constant function, that tells us that the derivative is equal to 0. So then that becomes a test we can use. If the derivative is positive, we know the graph has to be increasing. If the derivative is negative, we know the graph has to be decreasing. If the derivative is 0, we know the graph has to be constant. Here we have to find the intervals on which f of x equals 3/4 x to the 4th minus 2/3 x cubed minus 1/2 x squared plus 5 is increasing or decreasing? So first we will want to find the critical points. And we know we do that by finding the derivative and setting it equal to either 0 or undefined. So f prime of x, we will be using the power rule, and we have to do 4 times 3/4. Well, the 4 is going to cancel, so we will get 3x to the third minus, this 3 is going to come out front, cancel with the 3 in the denominator, and we would have 2x squared minus the 2 from the exponent here will cancel with the 2 in the denominator there, and we will have a minus x, and then of course the derivative of 5 is 0. Now this can be factored. Let's take out the greatest common factor of x, and we would have left 3x squared minus 2x minus 1. Now this, of course, factors, so we are going to get x times the quantity 3x, and of course here, first we'd have to have x. Now the way to get 1 is we're going to put a 1 and a 1, and then we just have to get the signs right, because we know 1 will be positive and 1 will be negative. We need a minus 2x here in the middle, so that means we need 3x to multiply a negative 1 and the x to multiply a positive 1, so our factoring is 3x plus 1 times x minus 1. And we know that we want to set that to 0 or does not exist in order to find the critical numbers. So this is going to equal 0 whenever x is equal to 0, whenever x is equal to negative 1/3, and whenever x is equal to 1. And since it's a polynomial, it's never going to be undefined. So these three are the critical numbers. So then what we do is take the critical numbers and create a sign line graph to determine the sign of f prime in each interval. So we put negative 1/3, 0, and positive 1 on the number line. We know that f prime is equal to 0 at each of those locations. And what we're going to do now is use test points to decide whether f prime is negative or positive in each of these intervals. So go ahead, pause the video, try this one on your own, then restart when you're ready to check your answers. In this first interval, we could use negative 1 as a test point. So we would have a negative here, this one would be negative, and this one would be negative. A negative times a negative times a negative is a negative. So that means f is decreasing on that interval. And you can either write out the word decreasing or you can just use a downward arrow. In this interval, we could use something easy, maybe like negative 1/6 as a test point. So this would be negative. If we put a negative 1/6 here, then this would be negative 1/2 plus 1. So this is going to be positive. So far we have a negative times a positive, and if we put a negative 1/6 in here, this is going to be negative. So a negative times a positive times a negative is going to be positive, which means the graph is increasing there. A test point in here, I would probably use positive 1/3. And again, I'm using 1/3 and 1/6, those kind of numbers, since we have a 3 here. I want to use values that are easy to simplify with that 3. So if we have a positive 1/3, this would be positive, this would be positive, this would be negative. So in this interval, the derivative is negative, which means the function is decreasing. Now over here, we could use a test point of 2, or 100, or 1,000, or 1,000,000, but 2 is fine. We would have a positive times a positive times a positive is a positive, which means the function would be increasing. So now, if we want to name the intervals where f is increasing, we look for where the derivative is positive. That happens on this open interval from negative 1/3 up to 0. Notice we can't include the negative 1/3 or the 0 because the derivative is not positive there. The derivative is equal to 0 at those two values. So we have to exclude negative 1/3 and 0 from the interval. Union, we see the derivative is also positive over here on the open interval from 1 to infinity. And again, we cannot include the 1 because the derivative is not positive there, it's 0. Then, to name the intervals where f is decreasing, we can see that happens here from negative infinity up until negative 1/3, open interval, union, the open interval from 0 to 1. So that's how we can use a sine line graph to determine where f is increasing or decreasing. And be sure to understand the concept here. If the derivative is negative, then f is decreasing. We don't say f prime is decreasing. We don't know if f prime is decreasing. If the derivative is negative, we know that f is decreasing. If the derivative is positive, we know that f is increasing. The first derivative test, which you can abbreviate FDT, finds relative extrema. So that means it will find relative maximums and relative minimums. Let f be continuous on an open interval containing a critical number, c. Now remember, critical numbers are where f prime of c equals 0 or f prime of c does not exist. And let f be differentiable on the interval, except possibly at c. And we have to say that part because, of course, if the derivative does not exist at c, that means f is not differentiable at c. But f has to be differentiable everywhere else on that open interval. The point c, f of c, will be a relative minimum if f prime changes from negative to positive at c. Let's take a look at this graph here. We know that f prime of c does not exist because of that sharp turn there, which means c is a critical number. So on the sine line graph, for f prime, we know at x equals c, the derivative does not exist. Now, to the left of c, we look at the graph and see that it is decreasing. We know that means the derivative is negative, and we indicate that f is decreasing there. After x equals c, we know the derivative is positive because f is increasing. So if f prime changes from negative to positive at c, that's what's happening here. F prime is changing from negative to positive at c, then this is going to be a relative minimum. And the point would be the point c, comma, f of c, which is what we set up here. Let's look at this graph now. F prime of c is going to be 0 because of the horizontal tangent that would exist there. So on the sine line graph, we note that f prime is 0 at x equals c. To the left of c, the graph is decreasing, so we know that f prime is negative. To the right of c, f is increasing, so f prime will be positive. So when we have this situation where the derivative changes from negative to positive at x equals c, we know that there will be a relative minimum at the point c, f of c. Now, the point c, f of c will be a relative maximum if f prime changes from positive to negative at c. So looking at this graph here, because of the sharp turn at x equals c, we know f prime of c does not exist. So let's put that down on the sine line graph. Now, coming into c from the left, we see the y values are getting bigger, which means f is increasing and the derivative is positive. To the right of x equals c, the graph is decreasing, and so that means the derivative is negative. Whenever the derivative changes from positive to negative at a critical number, we know that the point c, f of c will be a relative maximum. Here in this graph, f prime of c is going to equal 0 because of the horizontal tangent that would exist there. So let's put that down here on the sine graph. F prime of c is 0. Coming into c from the left, f is increasing, which means the derivative is positive. Going from c to the right, the graph is decreasing, which means f prime will be negative. Analyzing the sine graph, when f prime changes from positive to negative at a critical point, that means we will have a relative max. Now we can use this to find relative extrema on any function. And furthermore, that helps us create the graphs of these functions. Here we have to find the relative extrema of f of x equals radical 3 over 2x plus sine of x on the interval from 0 to 2 pi. Now, to find the relative minimums and relative maximums, first we need to find the critical numbers. And we know that critical numbers happen whenever the derivative is either 0 or does not exist. So let's find f prime of x. The derivative of radical 3 over 2x will be radical 3 over 2. The derivative of sine of x is cosine of x, so we add cosine of x, and we want to know whenever that's going to be 0 or does not exist. So if we solve radical 3 over 2 plus cosine of x equal to 0, we get that cosine of x is equal to negative radical 3 over 2. Now we know that that happens infinitely many times on the graph of cosine of x, but remember, we are being limited to the values of x between 0 and 2 pi. Cosine of x is going to equal negative radical 3 over 2 whenever x is equal to 5 pi over 6 or 7 pi over 6. Those are the only two x values on this interval where cosine of x will be negative rad 3 over 2. And the derivative will be a dne exactly never, because cosine of x exists everywhere. So this will never happen. So then that means we have these two critical numbers. So let's make a sine line graph for f prime. We know that we have to contain the left endpoint to x equals 0 and the right endpoint to 2 pi, because that was the interval we were given. Then we put these two critical numbers on there, 5 pi over 6 and 7 pi over 6. We know at these two critical numbers, 5 pi over 6 and 7 pi over 6, the derivative is equal to 0. So let's put those values on the sine line graph. Now we have to pick test points and decide if the derivative will be positive or negative in those intervals. So in this first interval, to pick a test point, maybe you'd like to picture the unit circle. Between 0 and 5 pi over 6, we have a really convenient test point, and that's pi over 2. So let's use that one. We know that the cosine of pi over 2 is 0, so then f prime would just equal rad 3 over 2, which is a positive number, which means f will be increasing in that interval. Between 5 pi over 6 and 7 pi over 6, we could use a test point of pi. We know that the cosine of pi is negative 1. And radical 3 over 2 minus 1 is going to be a negative number. So then we know f will be decreasing on that interval. On this interval, we have to pick a test point between 7 pi over 6 and 2 pi, and a really convenient one would be 3 pi over 2. We know the cosine of 3 pi over 2 is 0, so that means f prime would be rad 3 over 2, which is a positive number. And that means f will be increasing. Now, using the definitions we just learned, if the derivative changes over from positive to negative at a critical number, then we know that we will have a relative max there. So we have to evaluate f of 5 pi over 6. Remember, we plug into the function to find the y value, so that will be radical 3 over 2 times 5 pi over 6 plus the sine of 5 pi over 6. So this is going to equal 5 pi radical 3 over 12 plus the sine of 5 pi over 6, which is a half. Now we need the common denominator, which of course is going to be 12. So we multiply that second rational expression by 6 over 6, and we find out that f of 5 pi over 6 is going to be 5 pi radical 3 plus 6 over 12. So f has a relative max at the point 5 pi over 6 comma 5 pi rad 3 plus 6 over 12. Now going back to our sine line graph, we see that the derivative changes from negative to positive at the critical number 7 pi over 6, and that tells us we will have a relative minimum there. So we need to evaluate f of 7 pi over 6. So that will be radical 3 over 2 times 7 pi over 6 plus the sine of 7 pi over 6. And that's going to equal 7 pi radical 3 over 12. And the sine of 7 pi over 6 is negative a half. So we subtract 1/2. Of course, we have to get the common denominator. So we multiply by 1 in the form of 6 over 6. And this becomes 7 pi radical 3 minus 6 over 12. So then f will have a relative minimum at the point 7 pi over 6, comma 7 pi rad 3 minus 6 over 12. So f of x equals rad 3 over 2x plus sine of x will have two relative extrema. We found a relative max at 5 pi over 6, comma 5 pi rad 3 plus 6 over 12. And we found a relative min at 7 pi over 6, comma 7 pi rad 3 minus 6 over 12. In this example, find the roots, relative extrema, and sketch the graph of f of x equals x to the fourth minus 4x squared. Of course, roots occur whenever the function is equal to 0. So we would solve x to the fourth minus 4x squared has to equal 0. We can factor out an x squared, and we would have x squared minus 4 equals 0. Now, of course, this factors. It's the difference of two squares. So we have x squared times x plus 2 times x minus 2 is equal to 0. So from this, we get x is equal to 0, -2, or 2. So then that means we will have roots at 0, 0, -2, 0, and +2, 0. So we can get those on the graph. 0, 0, we have a root, -2, 0, and 2, 0. Next, we will do the first derivative test, and that's how we will find the relative extrema. So, of course, to do that, we need to take f prime and set it to 0 or undefined to find the critical numbers. So f prime is going to equal, we've got 4x cubed minus 8x, and let's factor that. We can take out a 4x, and we will have left x squared minus 2, and we have to set that equal to 0 or does not exist. Now, solving this derivative equal to 0, that will happen at x equals 0 or x equals plus and minus radical 2. And for when this derivative would be undefined, that's going to be never, because it's a polynomial. So these are the critical numbers that we need to get on our sine graph. So x equals 0, and when you're making your sine graph, make sure that the x values line up with the x values from your graph. So x equals 0 would be here. We know the derivative is 0 there. Then we have to plot x equals plus and minus radical 2. Now we know that radical 2 is about 1.4. So radical 2 is going to line up here. Let's bring that down on the sine graph. We know the derivative is 0 there. And then negative radical 2 is going to line up over here. And we can bring that down on the sine graph. We know the derivative is 0 there. Now we have to do test points. So from here, we could pick a test point of -2 or -3 or -1 million. We plug that into the derivative. Say we're going to use -2. This would be negative. Putting a -2 in here, it would square and become 4. Subtract 2, that's going to be positive. So a negative times a positive is a negative, which means the graph will be decreasing. Between negative radical 2 and 0, we have a convenient test point here of -1. So this would be negative. And if we put it in here, this would also be negative. Negative times negative is a positive, which means the graph will be increasing. Between 0 and radical 2, we can use a test point of 1. We would have a positive times a negative is a negative, so the graph will decrease. And in the interval from radical 2 to infinity, we could use positive 2. We've got a positive if we plug it in here, and we get another positive if we plug it in here, So that's positive, meaning f will increase. Next, we can analyze our sine graph. When the derivative changes from negative to positive at a critical number, we know that will be at a relative minimum. So that means we need to evaluate f of negative rad 2. F of negative radical 2 is going to be negative radical 2 to the 4th power minus 4 times negative radical 2 squared. Now we know that rad 2 times rad 2 is 2, and then we have to do that again because we're taking it to the 4th power. So this is going to be 4. This negative rad 2 squared is going to be positive 2. So we have 4 minus 8, and that's negative 4. So that means we will have a relative min at the point negative radical 2, negative 4. And we can come over to the graph and plot that. Our y values here, negative 1, negative 2, negative 3, negative 4 would be here. So at negative root 2, negative 4, we will plot our relative min. And just looking at the trends from the sine graph, we see that f has to decrease and then it has to increase. So that makes sense that this would be a relative minimum. Now, analyzing this piece of the sine graph, the derivative changes from positive to negative. So we know that that's going to be a relative max. So that means we will need to evaluate f of 0, which is going to be 0 to the 4th minus 4 times 0 squared, which of course is 0. So we know there is a relative max at the point 0, 0. So now we know this point, which we've already plotted, is going to be a max. And again, that makes sense with what the sine graph is telling us. We knew it came down here, hit a min, it's going to come up here, hit a max, and then it's going to decrease again. Now, analyzing this last piece of the sine graph, if the derivative is negative and changes over to positive, we know that's going to be a relative minimum. So that means we need to evaluate f of positive radical 2, which would be radical 2 to the 4th minus 4 times radical 2 squared. Well, we're going to have 4 minus 8, which is negative 4. So we will have another relative minimum at the point radical 2, negative 4. We can put that on the graph, over to rad 2, down to negative 4. We know that will be a relative min. And that also makes sense with the sine graph that says we have to change over from decreasing to increasing. So now we are ready to draw the complete graph. Now we know this is the basic overall shape of our graph, and we just have to make it work with the points that we have. So f starts out decreasing till it gets to that minimum, then it increases to the maximum, then it decreases again to the minimum, then it increases forever after that. So this was the basic trend, but once we connected the points that we knew we had to have, we get this graph. Now later in this chapter, we're going to learn even more techniques that allow us to get more specific with how the graph behaves throughout its entire existence. But for now, this is a good sketch of what the graph will look like. In this example, find the roots, relative extrema, and sketch the graph of h of x equals x radical 16 minus x squared. Now, because we have a radical, we should first consider the domain of this function. We need 16 minus x squared to be greater than or equal to 0. Now this is the difference of squares, so it could be factored into 4 plus x times 4 minus x. That needs to be greater than or equal to 0. And to solve a quadratic inequality, we know that we should make a number line. And then we will use test points. So one of the roots is -4, and the other root is +4. And we want to know when this product will be greater than or equal to 0. So let's use some test points. In this interval, we could use -5, and we would have a negative times a positive is a negative. We know right at -4, it equals 0. In between -4 and 4, we could pick 0, and we would have a positive times a positive, which is positive. At x equals 4, it's going to be 0. And then if we pick a test point in this interval, say 5, we would have a positive times a negative is a negative. Now we need the product to be greater than or equal to 0. So that's going to happen on this interval, including the endpoints. So our domain is that x is in the interval from -4 up to 4. So if we go to our sine graph, we go -4 and +4, and we will never graph anything on the outside of that interval because the function doesn't exist. So our entire graph will have to be between -4 all the way up to +4. Next, we can find the roots. And we know in order to do that, we set the function equal to 0. So we will set x radical 16 minus x squared equal to 0. So from here, we would get x equals 0. So we know that's a root of 0, 0. From under the radical, we will get x equals 4 and -4. So we also have a root at 4, 0 and a root at -4, 0. So we can plot all of those right now. We've got a root at -4, 0, a root at 0, 0, and a root at 4, 0. Next, we want to do the first derivative test so that we can find the relative extrema. So we will need to find h prime and set that to 0 or does not exist. Now to find h prime, let's first rewrite it as x times the quantity 16 minus x squared to the 1/2 power. because we will need to use the product rule. So we know that's going to be f prime g plus f g prime. So h prime of x is going to equal f prime, which is 1, times g, 16 minus x squared to the 1/2. Bring down this plus sign. Then we have to do f, which is x, times g prime, which will be 1/2 times 16 minus x squared to the negative 1/2. And then the chain rule says we have to take it times the derivative of what's inside, which would be negative 2x. So let's clean up this derivative. We will have the quantity 16 minus x squared to the 1/2. And then from this term, we will have a minus sign, and we have this 2 times the 1/2, so those will cancel, and the x times the x gives us an x squared out front, and then we would have 16 minus x squared to the negative 1/2. Now we're ready to factor. Remember, you always take out the smaller exponent, so we will be factoring out the quantity 16 minus x squared to the negative 1/2. And to do the factoring, you can just think of the division. We have to divide this term by this term, which means we're subtracting the exponents, and 1/2 minus negative 1/2 is 1. So we would have the quantity 16 minus x squared to the 1, which means we don't have to write the exponent. And you can always double check by multiplying it back out to get the original term. Then we have this minus sign that we have to bring down. And then from this term, we've factored out the 16 minus x squared to the negative 1/2, and we just have left x squared. We can write this now as a rational function. This 16 minus x squared to the negative 1/2 will go into the denominator as the square root of 16 minus x squared. And in the numerator, this is going to simplify to be 16 minus 2x squared. Now we can factor a 2 out of the numerator, and we would have quantity 8 minus x squared over the square root of 16 minus x squared. Now to find the relative extrema, we would set this equal to 0 or undefined. And we see that the numerator is going to equal 0 whenever x is equal to plus or minus the square root of 8, which simplifies to be plus or minus 2 radical 2. And this will be undefined at x equals plus and minus 4, which are the endpoints of our interval. And remember, we can't plug in anything beyond those because it would be out of the domain. So now we are ready to put our critical numbers onto the sine line graph. Now, when you're thinking about where radical 8 will fit in, we know that radical 8 is going to come between radical 4 which is 2, and radical 9, which is 3. So when you're plotting 2 rad 2, or radical 8, you're just going to pick a point somewhere between 2 and 3. So then if this is x equals -1, x equals -2, x equals -3, we will pick a point and call this -2 rad 2. We know the derivative is 0 there. Over here we've got x equals 1, 2, 3. So in between those two, we can plot positive 2 radical 2. And we know the derivative is 0 there. So now we will pick some test points. In this interval, between -4 and -2 rad 2, we have a convenient test point of -3. Now we know the 2 will always be positive. We know this radical is always going to be positive because we're staying inside the domain. So really, to do our test points, we just have to plug into this factor. If we plug x is -3 in, then we would have 8 minus 9, which is a negative number. So the function will be decreasing there. On this interval, we can pick our favorite test point, which is 0. If we plug that in here, we get a positive. So we know the function is increasing there. If we pick a test point in this interval, an easy one would be x equals 3. We see that this will be negative, and so h of x is decreasing. Now using the first derivative test, if the derivative changes from negative to positive at a critical number, we know that's going to be a relative min. And we will plug in to find the y value in just a minute. Continuing to analyze our sine graph, by the first derivative test, if the derivative changes from positive to negative at a critical number, then that means there will be a relative max. And so to find the point, we will need to plug in positive 2 radical 2 as well. So right now we know the overall general shape of the graph. It will have to decrease until it hits a minimum, then increase till it hits a maximum, and then decrease again. So now let's go ahead and find the coordinates of our relative minimum and relative maximum. Now to find the coordinates, we need to plug into h of x. So h of -2 radical 2 is going to equal -2 rad 2 times the square root of 16 minus -2 rad 2 squared. So this is -2 rad 2 times the square root of 16 minus, well, this is going to become 4 times 2, which is 8. So 16 minus 8 is 8. We know that 2 rad 2 is the same as square root of 8. So we just have negative square root of 8 times positive square root of 8. So that's going to equal -8. So that means we have a relative minimum at the point -2 rad 2, -8. So let's go ahead and plot that minimum. We go over to -2 rad 2, down to -8. We know that's going to be a min, and from our sketch, we know that's going to have a horizontal tangent there. We know the graph has to look like that at this point. We also need to evaluate h of positive 2 rad 2. So that would be 2 radical 2 times the square root of 16 minus 2 radical 2 squared, which is equal to 2 rad 2 times the square root of 16 minus 8, which is 8. So once again, we essentially have radical 8 times radical 8, which is going to be 8. So that means we will have a relative max at 2 radical 2 comma 8. So we can get that plotted on our graph. So we go over to 2 rad 2 and up to 8. We can plot our relative max. And remember, we know the overall shape here. Because of our sine graph, we know the function's going to increase, have a horizontal tangent where the derivative is 0, and then decrease. So we know that the shape of the graph at the max will look like this, and then we just have to connect the dots. There's nothing on the graph outside of -4 and +4 because of this domain. So then we know the graph will start at x equals -4, decrease to that minimum. Then the graph is going to increase all the way until it hits the maximum. We've got to go through 0 on the way, hit that max, and then decrease all the way to x equals 4. So now this is the complete graph with all the details we are able to get as of now. In the next section, you're going to learn how to get even more details, but for now, this is a good sketch. Now you might be wondering why we had to do a domain restriction on this problem for this h of x when we didn't have to do that on the previous graph. So let's take a look at that one. For this function, f of x equals x to the fourth minus 4x squared, we didn't have to do a domain restriction because the domain of any polynomial function is all real numbers. So there are no restrictions. X can be anything on the real number line. And that's why we didn't have to have a domain restriction on this one. But because of this radical, we did have to have a domain restriction for this graph.